Hi everybody, this lecture is going to be for section 17.3. The title is Conservative Vector Fields. The word conservative is used in politics a lot these days, but that's not what it means. It's talking about situations in which there's some physical quantity that's conserved. So I want to give you an example of that, a physical example, and then I think this will help motivate what's going on in this section a little bit. So the setup here is a very simplistic roller coaster ride. It's just a single loop, and it's high in the back of us, and then comes down low and goes high again up there. Now, when a car is at the top position like that and basically not moving, although with friction you need to have it moving a little bit to get it over the top, but basically think of it zero speed and it's way up in the air. That means its kinetic energy, KE, that's approximately zero. The energy that it has due to moving, and its potential energy, the energy it has because it's way up in the air, that's, well, let's just say large, maximum. Now, if you give this thing a nudge and it rolls down the track gathering speed, and when it gets down to right here at the bottom level, it's going to be going fast. That's the universal symbol for going fast. So I actually drew it bigger too. Well, it's closer to us, so that actually makes sense. Well, anyway, it's cranking along now, right? So now its kinetic energy is at a maximum, whatever that maximum is, and its potential energy, it's at ground level right now, so it has no energy due to its physically being above us. So your potential energy is zero. So in a very real sense, the total energy is the same. It's whatever max is added to zero here, and it's whatever max is added to zero here. And what's actually going on, and the way to think of this is that total energy is conserved. That's the sense in which they mean it. Meaning, if you add these two up, you get the same number when you're at the top and when you're at the bottom. Or really, anywhere along the loop, you'll have the same total energy. If you were sort of halfway on your way back to the top, you would be much slower, but your potential energy would be much greater. So kinetic energy and potential energy just basically trade off as you go around this loop. And if there's no friction, that'll just continue, right? You can keep going forever, maximizing potential energy and then maximizing kinetic energy and in between, sort of some of each. Well, that's a great example of a conservative vector field. Why? Because we may not realize it, but there's a vector field laying around here. There's a vector field that's due to the gravity. It's actually, we probably don't want to think of the acceleration field, but rather the force field. So this thing has a fixed mass, m, and the acceleration of gravity applied to m is going to create a force. So you get the same force everywhere. In fact, this field exists all over the place. We only care about it where we're along this track, but there's this downward force that would be applied. If you put the car over here, there'd be a downward force applied to it. It would make it plummet into the ground. But while it's on the track, the downward force is resisted by an upward force on the track, and you get the whole interplay of physics that makes it speed up and slow down as it moves around. Well, that vector field is particularly nice. Now, the connection that we may not be seeing, but we've got to see, is that this traveling around this loop, that's the same as a line integral. In fact, you can think of it as two separate line integrals. And I think that's the way I would like to first talk about it. There's a line integral that follows from the top of the track down this left-hand side. And it ends right here where we're speeding along really fast. Let's call this side C1. The integral is the vector field dotted with, well, differential position. So when we do the integral of f dr over C1, we get some number. And that number is actually, this force applied to the thing has made the thing speed up, and it's going really fast here. We get this number max, basically, whatever the kinetic energy is when you're at the bottom. Now there's another piece of the puzzle, which is to go from where we currently are the rest of the way around the loop and come back up to there. So C1 ended right there, C2 is this other half. And in C2, we're still doing an integral of the force dotted with dr. The difference is that in this integral, the force was acting in roughly the same direction as the motion. Right? The object was going down, the force was going down. But in this integral, the force is going down, but the object is going up. So the way we usually would talk about it here is the field is doing work on the car until you get to this point, and then as you go up, the work that had been put onto the car is being expended, and that energy is being kind of returned to, being returned to the potential, right, used to raise the car up in the air. So this guy is negative, and that guy is positive. That's the real point. We've got a positive amount of work done, depending, there's always a problem with work because you have to think of it relatively. One thing is doing work on another, or is it the other that's receiving work from the work? There's a back and forth there. In any case, here energy is being put into kinetic energy, into the motion of the vehicle, and here energy is being subtracted from the vehicle and being used to create potential energy. So this guy is negative, that guy is positive. What do you get when you think about the combination of the two of them, going down C1 and then going up C2 to arrive at the top? You get nothing, right? The kinetic energy was 0 at the top, we sped up, and then we brought it back to 0 as we raised to the top, or I should say approximately 0. Negligible might be a better way to say it. So if you put these two loops together, a loop where or rather paths together, a path where you're adding to the kinetic energy of the vehicle, and then a path where you're subtracting from it, the two of them together is 0. So this is typical of a conservative vector field. Integrals around closed paths are 0. Cool. So let's get into it now. There's some terminology we got to learn, and then we'll give a bunch of examples of a conservative vector field, and then this particular vector field, the gravity field on a planet, that's almost too simple. It's actually a constant vector field, so it turns out easily to be conservative. But there's a whole category of fields that have this property, and they get used all the time in physics, and well, actually in pure math as well. So I'll give you a test for how to tell when a field is conservative, when it has this property that integrals around closed paths are 0. I just actually accidentally used a technical word there, closed. Maybe it made sense intuitively too. Closed just means it comes around back to where it started. Okay, so excuse the wall of text, but I copied down a definition out of the textbook, or I slightly rephrased it, but this definition, if you want to read it for yourself in the original, is on page 114. 1114. Page 1114. And it's a pretty important idea, although I'm going to go through the definition. I'm also going to give you some visuals that I think will make the ideas clear. So the thing we're defining is the notion of a simple closed curve, which is something we'll come back to a lot. So you start with saying a curve in C, in R2, or could be in R3, is given by a parameterization, a position vector, a function of time, where the time parameter runs between two endpoints, A and B. Now, the first part is we're going to define what it means to be simple. We say that C is simple if R of T1 is not equal to R of T2 for all T1 less than T2 in between A and B. What this is saying is if the T1 and the T2 are numbers in that range, and they're not equal to each other, well, one of them is smaller then, so you can just, really you can think of this as they're different. T1 and T2 are different. If the times are different, the positions should be different. Sorry, there's a missing vector hat right there. Okay? So you're never at the same position at different times. Another way to say that. That's simple. The curve C is closed if your position at the left endpoint A is equal to your position at the right endpoint B. That is, T ranges between A and B, and you're at the same spot at A as you are at B. In other words, you return to where you began. Another way to say it, your terminal point is equal to your endpoint. So let me do as I was promising I would do and give you a bunch of examples of that. The kinds of curves that are not simple and not closed, and well, I guess ones that are simple and closed. So simple and closed is easy. It's a loop. That's simple and closed. It could be a much more interesting loop, right? You could have a loop that did something like this. Fine. Those are both simple and closed. If I wanted to be simple but not closed, what was I thinking? I want to be simple but not closed. Oh, that's not bad too. Don't run over yourself, so you can do all kinds of craziness, but don't return to the same point. That's simple but not closed. So we have a different terminal, and the initial point and the terminal point are different. How about if I did not simple but closed? That's good. That would be like, go off here and do some stuff where you end up crossing over yourself. These are different times where you're at the same spot. Right there, here, and here. But we did return to where we started. So that is not simple but closed. And if you want to be neither, I guess that's fairly obvious too. You need to begin and end at different places, but also have some of this self-intersection. So you'd start here and do something like that, for instance. So that would be not closed. Simple, but well, that one's not either. Sorry. Not simple, not closed. It turns out you can often work around things that are closed but not simple. You can sort of figure out a way to fix things around those self-intersections. But definitely your life will be much easier if you've got simple and closed curves. The next thing is going to be about the sort of domains of the vector fields we're concerned with, the regions over which the vector fields are defined. Let me just give you a simple example to begin with. Suppose you had this unit circle and you thought about the interior of that unit circle, so the region in the xy plane inside of the unit circle. There's the axes. You might have a physical situation where you defined a vector field just inside that circle. I don't know, maybe it's a bunch of vectors that rotate around and cause a flow of whatever it is inside that the vector field represents. This is a perfectly reasonable kind of thing, and this is the type that's called simply connected. Closely related to that, but different, and so not simply connected, would be if you had sort of a trough. So there was an outer circle and an inner circle, and maybe there's water in this region in between the two things. So it's like an endless stream. You could go around in a circle. Right? Think as a swimming pool with an island in the middle. You can have a flow in there too. Now these two regions have a fundamental difference between them, and it has to do with simple closed paths. Suppose in here I have a simple closed curve. It begins here and it goes around and it comes back to there. There's an idea called contractibility. And it has to do with, this has to do with the mathematical discipline called topology. And if people are thinking about going on to study more math beyond calculus, I highly recommend topology. It's really one of the coolest areas of math. You can get to reason very accurately about things that you would almost not believe you could turn into math. I mean, it's actually kind of an amazing, almost magical discipline. In any case, in topology, you think about what happens when you allow things to slowly, continuously deform. So, for instance, this path here, I could move off of that path just a little bit and have another path parallel to it that was very similar to it. The integral around one might be very close to the integral around the other. But I could keep going like that. I could deform that path into this one, and then deform that path into that one. And finally, I could shrink it right on up until the path went away. That the path literally was just a stand in place and kind of spin around in a circle, you know? That's called contractibility. This path can be contracted away. You might think about it as it's made with string, and the string is passing through a little, I should try to draw this. You've got a little, one of those eyelets, a little screw thing that has a whole, the wire's bent into a loop like that. If you run the string through that loop, go around the path, and then run it back out here, well, you could just pull on the strings and the path would go away. Now, that is not the case if we're in the other situation. If I had an initial point, we'll think of that as one of these eyelets, and some string coming in here. If I took the string around this and then pulled it out, when I tried to pull on the ends, it would get stuck. So this path is called not contractible, whereas that one is. Well, that's the difference between a simply connected region and a connected region. Although I should probably say what connected means first. Both of these are connected. The idea of connectivity is simply that there is a path from any point to any other point. If I name, here's a point A, and here's a point B. There's a way to go from A to B and stay in the region. In fact, because this region is non-contractible, there is essentially two distinct ways to go from A to B. There's one that goes around that side of the hole in the middle, and there's one that goes around that side of the hole in the middle. If on this guy I put a point A and a point B, and I'm trying to say this by, or illustrate this by making you think they're arbitrary. I could put them anywhere, but while there's multiple paths I could draw, like that, they're not really that different, because the region in between them, I know it's got all this crap drawn on it, but the region in between them is all in the area between them is all in the region we're talking about. So in the topological way of looking at things, you could slowly morph this one into that one. You could just move the string around is a good way to think about it. So in a situation where loops are contractible, you can also think of paths being what's known as homeomorphic. One can be turned into the other by continuous transformations. Here, there's no way you're going to turn this path into this path, because the hole in the middle is an obstruction to you. So let's give some examples of connected and simply connected, and then not simply connected regions. I guess we should do all four options. What are the possibilities? We could have not connected. We could have connected, and we could have simply connected. Let's do all three of those. A not connected region might consist of, for instance, of two disks. There's no, if you have a point A that's in this disk and a point B that's in this disk, no problem, you can get a path. But if your B is over here, let's call it B prime, you kind of hit the wall. You can't get to there. Not while you remain in the region. So, what do you do while you're trying to get to B? There's a gap in the region. Sorry, I probably should have striped this or something so you get the idea that it's the interior of these two disks that is the region we're talking about. So that's a not connected thing. A connected thing can be really squirrely looking. Like, for instance, I could have something like that. It can be very ugly, but actually that one is even better than connected. It's simply connected. Anyway, let's see the connectivity on it. Here's a point A. How about over here is a point B? I can get a path that stays in that region and goes from A to B. I just have to work my way around. And there's lots of them. They would all be sort of equivalent to one another. All right, and how about if we give an example where it's connected, but it's not simply connected? I already showed the trough thing. That's the basic idea. If you want to be not simply connected, you have to have holes. You might be sort of arbitrary looking, but if there's any regions that are excluded, any holes in the middle of your thing, then that's not simply connected. The problem is thought of in either one of two ways. If A is here and B is here, you can think of there are two sort of different ways of going from A to B that can't be morphed one into the other. Or you can think of it as put that together and turn it into a loop, and that loop can't be contracted. Either of those is fine. So a region with holes in it, not simply connected. A region that's contiguous but has no holes, simply connected. If the region falls apart into multiple parts, then not connected at all. This all is a little bit tougher in 3D and definitely harder to visualize. But there's some things we can do. Certainly, you could think about a disconnected region would be maybe a couple of spheres that are disjoint from one another. And so if that's disconnected, fine. So if there's really a line or a plane that you could draw in between parts of the region, then you've got disconnected or not connected. Simply connected would be one of these, just a sphere, or anything that could be morphed into a sphere. But to get not simply connected, you have to get a little bit stranger. The easiest thing that's not simply connected is a shape that topologists call it torus, but I think most of us would call it donut. Right? It's a body that has a hole that goes through it. Now that's supposed to be a solid region, so I can't quite draw the things, but if point A was over here inside of the donut, inside the body of the donut, and point B was over here, again, in the interior of the donut, and I don't know, imagine you're some sort of insect that eats through donut material. Could you work your way from A to B, digging a tunnel through the donut? And I don't mean work your way out to the surface and emerge and then eat your way in. That wouldn't be cool because you're leaving the region then. But is there a way to stay inside the interior of the donut and go from A to B? And there is. You could go around that back part, or you could go around this front part. And I hope you can see that when you put the the two of those together, well, reverse the orientation of one of those paths and then put them together, you get a loop. And that loop could not be contracted while staying inside the dough. It would have to remove it, have to come out into the hole if you were trying to contract that loop away. There are other examples of not simply connected regions, but the easiest thing is a donut, or you can sort of make multi-donuts. I don't know, maybe a cruller. You can create a donut that has two holes, for instance. Something like that. There's lots of fun to be had in going to higher genus donuts. This is called genus 1. Basically, genus is what topologists use to measure how many holes does a solid object have in it. So I have to tell you a bad math joke. There's a saying that a topologist is a mathematician who can't tell his coffee cup from his donut. And the reason is, if you think about the shape of a coffee cup, well, it usually has a little handle on it, right? That's basically a torus. To a topologist, it certainly is, because they think entirely in terms of things morphing, continuously deforming into one another. I didn't make the handle of that look right, but the hole in the donut and the hole in the handle of the coffee cup, that's the one hole that's in both of these bodies. Some people think of the interior, the place where the coffee goes as a hole, but it's really not from a topologist's point of view. The cavity in there where the coffee goes isn't a true hole, in that it doesn't prevent you from moving one path into another path that's within the body of that object. There are multiple animations you can see if you do a little Google on coffee cup and donut, and you can watch a coffee cup being morphed into a donut. It's not all that impressive, but hopefully you can visualize it on your own. Okay, so we've got simply connected regions. We're almost always going to work in simply connected regions. Okay, so these funky things, donuts and disconnected regions, won't show up. So next we're going to talk about conservative fields, that is vector fields that are conservative, and you should think that they're like the gravity field in the sense that there's some conserved quantity. In gravity, it's the total energy of a system that's conserved, but there can be many other conserved quantities. And in physics, they talk about a thing called the Hamiltonian approach, which means coming up with a function that tells you what the conserved quantity is, basically. And that's a really great high-level way to look at any system, is to know what its Hamiltonian is. Like, I don't know if you've done the basic physics before, but the potential energy, kinetic energy thing, that conservation of total energy is an amazingly powerful tool to solve all kinds of questions. So the book describes a conservative field as this. They say F is conservative if there is a function, a scalar function, that F is the gradient of. Let's call it phi, I think. For some scalar function phi. Just not sure if I should make my fees look different from one another. It should be the same. All right. So there's another way to think about, or to define a field being conservative, and it's okay because both of the things, I'm about to write the second one down, they're equivalent to one another, but they sound totally different. So let's make this, call this 1 and this one 2. F is conservative if, still the same first line, Every path integral, or every line integral around a simple closed curve comes out 0. Totally different things, and yet they turn out to be the same. So I feel like I phrased this wrong. I probably should have said for every simple closed curve, the line integral around it is 0. That might be a better way to say it. But yeah, I guess it's the same. Yeah, so we have seen examples, once in class and one out of class, of curves where we did an integral around a simple closed curve. In fact, it was the unit circle. One of them came out 0, and the other came out, I think it was 2 pi. So let me put those back on the board. Okay, so on the left side of the board, we have one vector field, and on the other side, a different vector field. And in both of them, see how it says C is the same. The unit circle is going to be our simple closed curve. So parameterized by cos t sine t, and that's t running from 0 to 2 pi. That's what makes it closed. We make it all the way around the circle. So the difference between the two sides of the board is the vector field. And the difference between the vector fields is just a minus sign here. This is negative yx, and this is yx. And you can probably almost visualize what the path integral, or line integral, as we pass around this the full circle is going to be. So I've drawn representative vectors, the parts of the vector field, at each 1/8 of the way around the circle. But you see, at first, the vector field is flowing in the direction of the tangent vector, and then it's orthogonal to it. Now it's against it. And it's orthogonal, now it's with it. Orthogonal and against. The againsts, the orthogonals here, and here don't add anything. And the withs are here and here, and the againsts are here and here. There's a balance. There's just as much plus as there is minus in the way the arrows point either with or against the tangent vectors. So for this guy, the path integral around our curve of f dr, that's 0. As much plus as there is minus, it's going to balance out and you get 0. Whereas on this one, we did the path integral around the curve in previous lecture, and we got 2 pi. So that one is conservative, or at least, well, you would know it was conservative if this was true for every possible simple closed curve. I've got one simple closed curve, so that's evidence that it might be conservative, but it's not quite enough. Nevertheless, this actually is conservative. And this one, well, it's enough to have a single simple closed curve where the integral doesn't come out 0 to know that it's not conservative. So because of that 2 pi, you know it's not conservative. I just want to make sure I'm clear on that this is a done deal. Once you know that you've got a simple closed curve where the integral doesn't come out 0, definitely non-conservative. This, it's still in question, but it's likely, it's more likely to be conservative, I suppose. Anyway, this doesn't contradict that it's conservative for sure. Okay, so what is the difference? Well, think about the other part of the definition. Well, I shouldn't say part. The first definition, the one that's given in the book, it said a field is conservative if it's the gradient of something. What is this field the gradient of? Can you figure that out? It's actually not so bad. If that's going to be the x partial and that's going to be the y partial, doesn't the phi have to be xy? Well, it's easier to check that in reverse. If you've got xy, the product of x and y is a function. When you take its derivative with respect to x, you'll get y. And when you take its derivative with respect to y, you'll get x. So that field is indeed the gradient of this phi, xy. Whereas could this be the gradient of something? Well, if it was, for instance, when you took the y derivative, you got x, that would imply you look like yx. But if you took the x derivative and you got y, that would imply you look like negative yx. Those don't jive together. So you see this is not anybody's gradient, whereas that one is. Well, I managed to talk us through, that one thing could be the gradient of something, whereas the other thing couldn't be the gradient of something on the last one. But in general, that's a little bit hard to decide. So fortunately, there's a nice convenient test for telling you when a scalar field is in fact somebody's gradient. When is it conservative? So if f is equal to the gradient of some phi, if that's the case, then, well, f's x-coordinate, I'm just going to do this in 2D for now, f's x-coordinate is the x partial of phi, and its y-coordinate is the y partial. So f looks like this. It looks like phi sub x and phi sub y. If that's the case, it does. So there's this really kind of nice thing that when you take the x partial and then do the y partial of that, or the y partial and do the x partial of that, that is, make the two mixed partials in the possible orders, you would get that if you took phi sub x's y partial, you'll get phi sub y's x partial. The results of those computations will be the same. So what that means is if you've got a general guy and you take the y partial of the x coordinate and the x partial of the y coordinate, they should come out equal. So let's just give f's coordinates names that are different from phi sub x, phi sub y, because there we're sort of presuming that it already is the gradient of something. So if f looks like, how about just f and g? And the f's, let's see, it's the f thing, the thing in the x position's y partial, should be equal to the thing in the x partial of the thing in the y coordinate, which is g. If that happens, if whatever's if you can form these partial derivatives of the x component and the y component of f, and they turn out equal, then you're in good shape. Then it could be the case that you're the gradient of something. Let's put it a different way. What if these were not equal to each other? So if f is equal to fg and f sub y is not equal to g sub x, well then there's no way, because if you came from being the gradient of some field or some scalar f, sorry, phi is the Greek letter for f, so that's kind of confusing. But if you are the gradient of a scalar function phi, then those partials in that mixed up order will be equal. So if you're just a general thing and they're not equal, you know that f and g didn't come from the being the partial derivatives of some scalar field. So if that particular computation doesn't work out, then f is not conservative. I'm just going to abbreviate conservative because I'm running out of space there. And it turns out that if it is, then there's a procedure that'll let you figure out what phi is. So, in fact, it turns out to be an if and only if thing. If they're different, then you're not conservative. If they're equal, then you are. Let's take a look at what that's a similar thing, that test for whether you're conservative or not. turns into when you're in 3 dimensions. So suppose you've got a vector field f and it's the gradient of some scalar field in 3 dimensions. Then f looks like phi sub x, phi sub y, and phi sub z. And there's lots of different ways to make the mixed partials from this. For instance, we'd have phi sub x y equals phi sub yx, just like when we were in 2D. But you could also compare, say, the first and last, and you'd get that phi sub xz should be equal to phi sub zx. And finally, what are these two? The second and the third one, you'd have that phi sub yz should be equal to phi sub zy. Now, again, that's presuming we started with something where f was the gradient of some field phi, or some scalar field phi. If instead you've just got a generic f, suppose f is equal to fgh, well, we got to see what these things translate into. This first one is rather like the thing we did in 2D. It's that f sub y, little f sub y, should be equal to little g sub x. All right, and then this one would be first and last, so that's f sub z and h sub x. And what is the last one? That's where we compare the second and the third things and taking the appropriate derivatives. So we'd have that g's z partial should be equal to h's y partial. Yeah. So more complicated, but it's really the same spirit, that the things that need to be equal, if these guys were first partials, are the second partials in the 3 different orders that we could make them. Well, 6 different orders, but 3 different pairs of things, y and x and z, y and z. If those things are all equal, then you've got a conservative field. So that is that all of these things imply conservative. And if any one of the 3 fail, non-conservative. Now we should talk about, supposing these conditions do match, that you know that the thing is conservative, well, how do you actually figure out phi? Phi is known as the potential function. So that topic is called finding a potential function, or simply finding a potential. But that's phi, when I say finding a potential. There's an example, well, we should probably do an example in 2D first, and then we'll do one in 3D, when we think of it. So let's see, here's an example of a vector field. It's let's see, 2xy plus e to the x. That's what's in the x coordinate. And in the y coordinate, it's x squared. So let's first just do our test to see if this could be indeed conservative. So that means we want to take 2xy plus e to the x and take the derivative, partial derivative with respect to y of that. And we want to take the partial derivative with respect to x of x squared. And we want to compare these two and see, are they equal? So we're taking a y partial on this one. That term involves a y, so it's y to the first power. Yeah, that's just going to become 2x. And then this is a function just of x, so when you take the y partial, it's like a constant, so it's 0. So this is equal to 2x. And it's maybe a little clearer that that one's equal to 2x as well. So this is a conservative field. Now let's go about actually finding what its potential function is. Yeah, so I think the simpler looking one is this one. So what I'm going to do is integrate that with respect to x. Excuse me, with respect to y. I'm in the y coordinate. So we're going to integrate, if we call those functions f and g, let's do that. We'll call this guy f and this guy g. I'm going to integrate g with respect to y, because if this is indeed the gradient of something, then that's the y partial of that thing. What do we do when we integrate something with respect to y? We treat x's as if they were constants, and functions of x as if they were constants. Great, so integrating x squared dy just gives us y times x squared plus something. Now the something, we usually write plus c, okay? But that's not quite the deal here. We're going to write plus a thing that would behave as a constant in this context. And that's anything that involves x's. So the thing that we get when we add the plus c is actually not truly a constant, but simply a thing that doesn't vary with y. In other words, a function only of x. Possibly a true constant, but also possibly a function of x. Let's call it c of x. C to make us think it's a constant, and then the of x to let us know that it's maybe a function strictly of x. Maybe the best way to think of this, then, is that we've sort of got a candidate for what phi of xy could be. It'll look like yx squared plus a part that's only a function of x. So let's assume that's the case. I guess I can get rid of that and this. I just want to save what's down at the bottom there. So the idea then is, I think phi of xy is yx squared plus this constant function, or this thing that behaves as a constant, the thing that's only a function of x. Yx squared plus c of x. Now, the thing that was in the x coordinate of our vector field, that was f. I just erased it. So let's just recall that f was equal to 2xy plus e to the x. I have to ask then, is this the x partial of that? Sorry, f, not f sub x, but f equal to phi sub x. So we're going to take the x partial of phi and compare it to our f. The x partial of phi sub x is 2x, or y times 2x plus, well, the derivative of c, whatever that is. Whereas f was equal to, I said 2xy, yeah, those are the same. 2xy plus e to the x. So what has to be the case if these two things are to be equal? The answer is yes, provided that e to the c is e to the x. It's really that c prime is e to the x, but then we would integrate and get that c was e to the x. So c with e to the x is pretty quick and easy. If not, we might have to do one last integral to figure out what c was. So then that means we actually now know what f is, or what, excuse me, what phi is. It's going to be 2xy, excuse me, 2xy plus e to the x. And then once you've got that form, it's really easy to take the gradient of it and say, yep, we sure do have that. The gradient of that sure is our capital F. So you see that's a bit of a process. You pick one side or the other of the vector field. You integrate it with respect to the variable that's, that it corresponds to its position. And then when you do that, you'll get functions that you'll get constants that are actually functions of the other variable. And then you do a little rigmarole to figure out what that function could be. They've got it laid out as a sort of a procedural thing. I'll just mention this. I'm not going to copy the procedure down, but see page 1117. If you want to see, there's a box on that page where it has a kind of layout of what to do. Let's do one example that's in 3D, because it gets a little more interesting in 3D. And I'm just going to use the one in the book, example 2. This is example 2 on page 1116. That's actually just part B. Okay, so I got to copy the function down. The gradient, the vector field down. 2xy minus z squared is your x part. The y coordinate is x squared plus 2z. And the z coordinate is 2y minus 2xz. Right, so the way we're going to proceed is we'll pretend this is the x partial of something, and so we'll integrate to figure out what that something was. We could just as well start with pretending this thing was the y partial of something, or rather this thing, or even this thing was the z partial of something, but I think it'll work just fine to go x, then y, then z, working across that way. There are circumstances where sort of beginning with one of the components of f will be easier than the others. But, all right, so we will integrate 2xy minus z squared with respect to x. If we're right, this should basically be phi. Or maybe think of it as that's a guess at phi. Because it's going to include an arbitrary constant of integration. So, well, let's see, what do you get when you integrate 2xy with respect to x? 2x becomes x squared, the y goes along for the ride, so it's x squared y. Minus z squared, well that's, with respect to x, that just becomes minus z squared x. And as I said, we're integrating with respect to x. That means we need a constant of integration that, well, I shouldn't say constant, really, but the thing that behaves as the constant of integration is something that's just a function of the other variables of y and z. So let's call it c of y and z. So that's what I think phi is. X squared y minus z, x squared plus some function of purely of y and z. Let's take the y partial of that and compare it to this. So phi's y derivative is x squared. The y derivative of that is gone, plus the derivative of whatever that constant function is. I better not just say derivative, but rather y derivative of that constant function of c sub y, c of yz. Okay, so contrast that with what we've got for the middle part of f, and it lets you know that, well, that c sub y of yz must be 2z. I'm just going to drop the arguments on there and just call it c sub y is equal to 2z, which means c is equal to, integrating with respect to y, we get 2zy. Well, not quite. Okay, so let me write the integral around then. We're going to integrate 2z with respect to y. And we will get 2zy plus a function of a thing that's a function strictly of the remaining variable. At this point, we've got no x's, right? Because we were dealing with this guy, which was a function only of y and z. That's only a function of y and z. It turns out only of z. Anyway, there's no x's involved, so the constant should be a function of just z. Let's call it d of z. So that tells me, what does that tell me? That tells me what this c of yz was. It's 2zy plus dz. So overall, we get that phi is equal to, what do we have for phi before? X squared y minus z squared x plus this c. But the c is 2zy plus a function of z. Cool. Well, I guess there's one last step to take, which is, well, let's just notice first, for one thing, if I take the x partial of this expression, will I not get 2xy minus e squared? 2xy minus e squared, and the other doesn't involve x, so that becomes 0 when you take the x partial. If I take the y partial of it, I'll get x squared, nothing, 2z, and nothing from that. So it matches for the, this thing's x partial is the x coordinate of f, and its y partial is the y coordinate of f. We've got one last thing to check, which is its z partial the z coordinate of f? Now the z partial will go to 0 here. Let's just go ahead and write out what phi sub z is. It's going to be 0, it's going to be minus 2zx, that term. It's going to be plus 2y from that next term. And it's going to need the z derivative of d of z. Let's just call it d sub z. Wow, well that's interesting. We've already got minus 2xz and plus 2y. So what's d sub z? 0. And that means this d sub z is actually a constant. Okay, or something. But in fact, since we don't care constants aren't going to affect any of these partials, we usually take this k to be 0. In fact, that would be good advice. Take anything that's a pure constant, not a function of other things, make it 0. All right, so, well, that means we've found our phi. If this last part is 0, I'll draw a box around it. It's this piece here. So finally, let's see, why are we bothering to find these scalar potentials for a vector field? It's because there's this frankly beautiful thing called the fundamental theorem for line integrals. All right, so the last thing we got to do is talk about the fundamental theorem of line integrals, which is basically why we did all that business of finding scalar functions. The scalar fields so that our vector field would be the gradient of them. So if you've got a conservative field with scalar potential phi, so if F is a conservative, whoa, my spelling just went haywire. Conservative with scalar potential phi, and you've got a line integral. Let's say it goes from a point A to a point B of f dr. That's poorly phrased. It shouldn't be and, but rather it should be then. Then the idea is your curve starts at a point A and ends at a point B. Well, you can do what looks like just like the fundamental theorem of calculus. Use the phi there as kind of the antiderivative of f. And so you evaluate phi at B, and you evaluate phi at A, and you subtract. And this is why this idea is so powerful in physics, in lots of things, but particularly in physics. You figure out integrals along paths through a vector field by just looking at the scalar potential at the two endpoints. That's pretty cool. And that's why, for instance, looking at total energy at the endpoints of a complicated interchange of kinetic and potential energy is enough. You don't have to worry about what actually happened during the course of your motion from A to B. You only look at the scalar potential at B and at A and subtract. All right, so that's where we'll leave it off for today.